So thank you everyone for having us. I'm David, this is Romain. We're going to be talking about the breadth of use cases from machine learning at Netflix. And we're not going to focus on the machine learning itself, but rather the infrastructure that we built to support all these diverse use cases. Just to give you an idea of some of the verticals that our team supports, the Metaflow team, we work on computer vision, something called content demand modeling, which we'll use as a use case and talk a little bit more detail about later. You're obviously familiar with recommendations and personalization being a very key part of our business. Intelligent infrastructure is something that is, over the past few years, really becoming a big use case. This is things like systems that parse logging, or just generally speaking, engineers starting to use more and more machine learning into their traditional engineering products. Payments and growth, ads, and we'll talk about content knowledge graph a little bit. Now, throughout the talk, we're going to refer back to a few specific examples to highlight some of the aspects of our architecture. This first one is identity resolution. We try to keep a knowledge graph of all actors, movies, and various entities in our space. And they have maybe different representations across different databases, maybe some missing data, different attributes, and things like that. This is a massively parallel computation matching problem to try to determine which entities belong to one another. We're also going to talk about media processing. On top of the Metaflow hosting part of our product that Roman's going to talk about later, we have a whole media processing system. So this is building infra on top of our infra. We're going to talk about content decision making. And this is a complex set of models that try to predict the value or the demand for different content across the entire life cycle of the content. This goes all the way from when we first hear a pitch all the way to post-service where we have actual viewing behavior. And all of these models need to be orchestrated to give one complete view of the world. We're also going to talk about a really interesting use case, which is kind of meta models. So these are models that are used to explain other models. And we're going to talk about dependency management as a driving factor for this use case. To give you an idea of the size of our platform, here are some numbers. To put it into perspective for Netflix overall, we are not the only machine learning set of tooling in Netflix, but we are the Python-paved path. So Metaflow is all about doing machine learning in Python. We have a whole separate Java Scala ecosystem that has historically been used for personalization and recommendations. If you're interested in that, we have lots of tech blogs, lots of Netflix research blogs on that topic as well. Now, we want to focus on some of the principles that we used when designing Metaflow. And they might be a little bit different. So everybody knows why we have platforms. I mean, there's obviously cost savings, consolidation of software, and a variety of sort of business-related things. But myself, I come from a neuroscience background, and so we started to think about what makes people productive, because machines are actually relatively cheap compared to people these days. And we want to minimize the overall cognitive load that someone using our platform experiences so that they can focus more on the machine learning. And what does that mean? It means reducing anxiety. It means having stable platforms that people feel comfortable operating, comfortable experimenting with. That helps them push their work. Reducing the overall attentional load. This means building software that doesn't draw attention to itself, but rather lets people focus their attention on their own work. Unlike this young woman here whose production ranking model seems to be a small part of this system that she's trying to wrangle. We also want to reduce memory. So we want to handle complexity on behalf of the user as opposed to push complexity back onto them. We'll go over a few principles that we've learned over the years. One of them is the house of cards effect. No one would be comfortable building their own system on top of this rather shaky looking house of cards. But there's another problem with that. Not everyone can stand on top of your system. You need a scaffolded system such that at any given point, they can tap off to do their own sort of project. You can't expect any machine learning platform to handle all use cases, but you certainly can allow people opportunity to build on top of your platform. Another one that we've seen over the years is the puzzle effect. You may have seen that many platforms have components and they all fit together, but they fit together in really non-obvious ways and maybe only one way, and that's more of a puzzle. What we would like to build are Legos, things where people can combine them in novel ways. And one thing that we do is have similar levels of abstraction, and interface aesthetics. And that gives you transfer of knowledge from one component to another. The waterbed effect is actually my favorite one. Engineers love to expose the complexity of their systems to other users. If you don't know exactly how people are going to use it, why not just give them all the options? Well, complexity is a bit of a fixed size volume, similar to a waterbed that has a fixed amount of water inside of it. So if you push the waterbed down in one place, it pops up in another. And we want to have that complexity pop up for us as the platform team, not for our users. So you can see this example of a overly complicated request, some sort of a web request API here, or a very simple one where we just made some of the decisions on the user's behalf. Now, Roman's going to go through an introduction to Metaflow, since we know that you're not all familiar with the basics.
Thanks, David. As David said, my name's Romain. I'll give you here a brief introduction of Metaflow. The goal isn't to make you a Metaflow expert, but just to allow you to understand the rest of the presentation. So at a very basic point, Metaflow just allows you to express computation. You have some input, you'll do some computation on it, and it'll produce some output. In Metaflow, this concept here that is represented is a step. We put these steps together in a graph, a directed acyclic graph, which we will call a flow. So as you can see here, you have a couple of steps. It starts at the start step. Once the start step is done, A and B can execute in parallel if they want to. Once both of those are done, then the join step can execute. And once that is done, the end step can execute. So that representation of the graph that you see on one side of the screen, it's coded up in Metaflow on the other side. We'll go in detail over some of these concepts here in the next few slides. But suffice to say that this looks like very regular Python code that any Python developer would be comfortable coding. There's no special DSL, no special constructs. It looks pretty natural for a Python developer. The important thing to note about how this graph executes is that in Metaflow, each of these steps will execute in an independent process or an independent node. And this is very important for Metaflow because this allows Metaflow to execute this flow either entirely on your laptop using different processes or across a cluster of machines using different nodes with no change to the user code. The same code that's on the right here, or on your left, or yeah, the right, will execute both on your laptop and on a cluster with no change in code. One of the main things that allows Metaflow to do this is how it handles data. So you can see in the code here that you have this variable x that goes through from the different steps, from start to A to B to join. And the value changes, but it's accessible in each of these steps. The way Metaflow does this is it basically stores in a persistent storage system like S3, that's the one we use at Netflix, the association between a pickled representation of the value and a hash of it, here in this case A4ABB6, and the name of it, so here x. So it says, okay, for the start step, x refers to this particular hash. And it'll do this for the rest of the steps, and it'll make it accessible effectively in all of the steps. We do this in a content address manner like this so that we don't store the same value multiple times. But this also means that effectively all the steps have access to the value, and you can also refer to them later. You can say, hey, what was the value of x in my start step for this particular run, for this particular flow? When you execute the flows, they will be transformed into runs. So a run is an instantiation of a flow. And we effectively give it a particular ID. Users can associate tags with it, and they're also separated out by users so that it's very easy to collaborate across different people in the team and keep your runs separate and also be able to refer to them later and figure out, well, what did this run do, and associate like semantic tags to it. As I said, I would go over some of the details of the code here. So you can see that in the first part, you can specify dependencies. We go over this a little bit later in this talk. David, right after this, will talk about both scaling and orchestration, which are highlighted here in terms of your code, where you can specify the resources that you need, as well as when you want your code to execute. We've already talked about the artifacts, the X. We've talked about parallelization, that you can see that A and B execute at the same time. Another thing that is useful that is not shown in this slide, but that is useful in the rest of the talk, is you can have multiple instances of the same step in a for each manner. So you can have, you can iterate over different inputs and the same step. Going back to some of the principles that David highlighted, Metaflow tries to focus on the bottom layer of the ML stack. So we want to allow the developer or the data scientist, and usually at Netflix it's other teams in the platform's teams that will do this, focus on the upper layers like model development, feature engineering, while we at the Metaflow team focus more on the infrastructure need. And usually the good thing here is that the data scientists don't really care about what the infrastructure looks like as long as it does what it wants to do. And we also don't want to constrain the data scientists in their model development as long as we can provide the infrastructure that they need. And this is even more important today with LLMs and other large compute, where people are very interested in doing cool stuff with models, and you need a lot of resources at the bottom. To finish off this section, I'll just give a brief history of Metaflow. It started out in 2017 at Netflix. I wasn't here at the time, David was. But I came around 2019 when it was open sourced at AWS reInvent at the end of 2019. At that time, we had effectively Netflix Metaflow and then an open source Metaflow, which were kind of separate. We had to rewrite part of it to do this. In 2021, a company named Outer Bounds was formed with some of the employees from Netflix that basically went out and created a company to support Metaflow in open source. It's still around. And at that time, we still had 2 versions of Metaflow, which was kind of difficult for collaboration. We finally merged it at the middle of 2021, and this is the state we're in right now, where we have effectively a common core that we use at Netflix. So the open source Metaflow that is out there on GitHub is the one we use at Netflix, and we add stuff to it. And other companies do too. So we release some of the additional extensions that we have in 2023, and a bunch of these other companies use it, including 2 known ones like Zillow, Moneyline, that actually built their own set of extensions to support their infrastructure. And to show what the infrastructure kind of looks like, you have a core that basically runs the graph that I explained earlier that allows you to access artifacts. And around it, we build things like data support, where we have S3 support, then you have Azure and Google Cloud. We don't use those. We use S3, and we add our own extension called Fast Data, which David will talk about as well. You have compute, where you can use Kubernetes or Batch. We don't use those. We use Titus, which David will talk about as well too. Schedulers, Argo, Airflow, step functions. We use Maestro. Environment management, which we'll talk about. There's a PyPy Conda decorator in open source. We use our own from the Netflix extensions. Outer Bounds released Fast Bakery. All this to show that these parts are effectively, we can pick and choose different parts. Again, with the Lego block abstraction that we talked about, that this allows you to kind of build the right approach for Metaflow. We'll talk about hosting, which is another part, and there's other components to Metaflow that we will not get to in this talk. Next, David will focus on the orchestration and the compute.
Okay, well, as Romain had mentioned earlier, you can run all of these jobs as a local process on your machine, but when you're scaling up and scaling out, that's going to be insufficient, although it's great for prototyping. So we rely on 2 also open source technologies. One, Titus. If you're interested in the details of Titus, you can look at some tech blogs we've produced over the years, but it's our in-house container and compute management system. It allows us to do something like shown here on my right, where I can request certain resources, number of CPUs, memory, and whatnot. We also need scheduling and orchestration. That is handled by another OSS product called Maestro. If you're interested in the details of Maestro, June from Netflix will be giving a talk, I believe, tomorrow on this topic. But needless to say, when you're going to production, you need to schedule this thing either to run on a chronological sort of every hour or every day, or through some sort of an event triggering system. And we'll talk a little bit about how the event triggering is used. But I do want to highlight one really important aspect of Metaflow is that prototype to production, as Romain said, all of the code looks exactly the same. So let's take a look at this example here. It does some sort of a large computation. It's just a very simple 2-step graph. But you'll notice that at the very top here, we have this schedule decorator. So at some point, we're expressing that we want this to run hourly. And we also have this resource decorator. And we're expressing that this start step here requires 480 gigs of RAM and 64 CPUs. And now the exact same code can run in these 3 different contexts. So, and this is all just through the command line interface. So if you just type your flow name run, it'll run everything in sub-processes on your local machine. You'll see logs and a variety of output. If you do run with Titus, we'll actually export Metaflow, land a code package in a container that was requested by the Titus system, expand the code package, and run your step on Titus. And the exact same code, nothing changed. Your dependencies that you specify that Romain will talk later and everything magically appear for you. You can even mix and match. Some steps can run locally on your laptop, other steps can run on Titus. And when you're finally ready to schedule this thing, you can do Maestro create. And now finally, the schedule decorator will be respected. And when you push it to the system, to the Maestro system, we will run this thing in an hourly cadence. As a way of understanding the complexity of the systems that we have at Netflix, we want to talk just briefly about content demand modeling. And this is about understanding the drivers for content across the life cycle, like I mentioned, all the way from pitch to post viewing behavior. And what we want to impress upon you here is that this is a very complex system. It has many machine learning models to take into account aspects across the life cycle of the content. And it also interacts with separate systems. So although you can't see the details in this slide, the gray boxes are external data sources that we get from other places. The green boxes are Spark ETLs that are wrangling large amounts of data to organize them into tables for machine learning. And then the blue boxes are all Metaflow flows that are actually doing machine learning and usually writing tables out as well. And Maestro allows the underlying signaling capabilities to support this kind of a graph. But interestingly, we don't really want to expose all the users to the complexities of Maestro. So just in the same notion as I had said earlier, from prototype to production, we developed some special syntax. And this syntax actually works across which system. So if you're using the Kubernetes integration with Airflow in the OSS, the syntax here is the same. Again, back to this Lego sort of plug-in architecture. And if you're just connecting one flow to another, it's very simple. We just have this trigger on finish decorator. And under the hood, we expand this into the whole complex signaling system that Maestro supports. We have other mechanisms to listen to arbitrary signals, and they have a very similar syntax. And that's how you can create the graphs, the sort of complex graph that we showed previously. We're going to move along to a different component. This is one that I have worked on quite a bit, and I'm quite proud of. It's called fast data. Let's go into some of the details. What is fast data? Fast data is about getting memory into your Python process very quickly. So many companies, probably yours, have some sort of a data warehouse. There's probably some sort of SQL engine behind it, and that's all great for all of your large-scale data wrangling and preparation. But at some point, you need to actually do something in Python, and so you need to get that data into your Python process. And the use cases here might be some last-mile feature engineering or actually training your model. And so we provide two abstractions, Metaflow Table and Metaflow Data Frame. Metaflow Table is an abstraction that represents data in the data warehouse. At Netflix, our data warehouse is an Iceberg, an Apache Iceberg table. If you're not familiar with Iceberg, it's a metadata layer on top of raw data files. And it's really great for us because it is kind of independent of any engine. So you can sort of implement your own engine, which is what we have done. The raw data is Parquet files, and those live in S3 like most everything at Netflix. Below that is in the user space, so the table in memory. This is in your Python process. And here we have a hermetically sealed, dependency-free Parquet decoder built on Apache Arrow. We'll go into some of the details of how that works in the coming slides. But we're not reinventing Parquet decoding. We're using what is out in the open source community. And your whole goal here is to get the data into your Python process as fast as possible, and then probably convert it into one of your favorite frameworks. We're not super opinionated about which ones data scientists use. Here I'm showing Pandas, or my new favorite framework, Polars. And then also we have a custom C++ layer, as there are some operations that are specific to Netflix that we can just do better if we implement them ourselves. So as I had mentioned, the remote tables in the Netflix data warehouse are Iceberg tables. And here's just some really simple syntax about how you can get some data into your Python process. So we instantiate a table with a name, in this case, the namespace DSE. The table is called myTable. And I want to just grab data from one partition. This would be the equivalent SQL of a select star from dse.mytable where dateint equals that date. But we're not actually running any query engine. We are parsing the Iceberg manifest files ourselves, finding the data files that correspond to this partition, downloading them directly to the machine, and then decoding them. Now, I just described the remote table representation, and now let's take a look at the Metaflow data frame, the in-table representation. So here in this little code snippet on top, we're again using the table object. This getAll function will just grab the whole table. And then here we're using one of those high-performance C++ operators that I had mentioned. This one's called take. It's very simple. It selects rows. In this case, we're using the column is active, like if you're an active member or not, to select those rows and create a new data frame. Eventually, you can convert it to polars or pandas. Now, what's so special about this Metaflow data frame is that it's completely sealed and dependency-free. And what do I mean by that? I mean that we actually have our own version of Apache Arrow. It's just their OSS version of Apache Arrow that we fixed to a particular number. We control the entire compilation, add some of our own custom code in, and we create a very fat binary called metaflow data.so. It's a Linux shared object. We actually ship this along with Metaflow. This means that we don't download any packages. We don't have any dependencies on any external software. You might be asking, why did these people not just use Apache PyArrow? That would be the natural way of decoding Parquet in Python. Well, the problem is that our users might want to use Apache PyArrow, or their software that they're using, like TensorFlow, may have a dependency on it, and we don't want our dependencies to step on the dependencies of our users. So we are isolating them from how we do the Parquet decoding. Interestingly, this means that we can change the implementation under the hood and no one will see a difference. I want to give you a few numbers here about how this is used. You can see in 2023, we had quite a lot of usage of this piece of software, but more importantly, the throughput. In this example that I created here, we scan 60 partitions, download the Parquet, do the parallel decoding using the Metaflow data frame. It was about 76 gigabytes uncompressed on a single machine, and I get throughput of about 1.7 gigabytes per second. That's actually really close to the throughput of the NIC on this particular machine. I have some other performance examples here we won't go into too much. This top one, a select account from user.table, is just showing that this fast downloading method in bypassing the query engine is much faster than what people were doing before using Presto or Spark. And the last two graphs are showing that our C++ implementation of filtering is much faster than what you would achieve if you were using pandas or something like that. We still encourage people to use pandas or polars or whatever software they want, but we provide a few heavy lifting operations that they can do before converting to those more convenient frameworks. Now, by way of demonstration, I want to talk about a content knowledge graph. And as I had mentioned earlier, this is a process that matches entities across different database representations, and they may have missing data, incorrect data, different attributes, whatnot. Creates a bipartite matching graph problem. And it requires daily, if that's the frequency at which we want to run it, over 1 billion matches to be computed. It's embarrassingly parallel, but quite high scale. And here's a Metaflow graph that sort of shows the overall architecture of this. We have an input table that is sharded by a reasonable quantity, like the hash of the rows. And this gives us a bunch of different partitions. We can spread those partitions out in a Metaflow for each. So each one of these nodes in the center is getting a different subset of the matching problem. We use the table object to read the data in, Metaflow data frame, and whatever other software you want to process it. And then similarly to reading, we have tools to writing back out to the Iceberg data warehouse. And all of this is done in compliance with our Netflix data warehouse, which is usually like the Spark system. Let me show you a little bit about what that code could look like. This is not the exact matching problem, but structurally, it's the same as the graph I showed you. We have some ways of getting all of the Parquet shards as groups. So in this case, we want 100 groups. That means that we are going to spin up 100 containers to run this process function, where we grab some data, load the Parquet. In this case, I'm just showing grabbing the number of rows of from the data frame, and then join the graph back together, and you can do something with all of the results that you just computed. Okay, Roman's going to take over and talk to you about Metaflow environments, which is the way that we can keep things consistent across all of these different compute substrates that we have.
Thank you, David. So yeah, Metaflow environments. What is the problem we want to solve? The basic problem is that we want our data scientists to be able to have reproducible experiments. So if they run something today, then a week later they can get back to it and they can run it again and observe the result, or even a month later, they can go and say, hey, what was the model like? What artifacts did I produce in this result? That's great. Unfortunately, the world keeps moving, and so it makes it hard to do, and the solution that data scientists had been using before to kind of keep their environments the same was something like pip install my awesome package. That works until my awesome package decides to become less awesome and depend on a package that you didn't depend on and break your whole system. So environments basically solve this, and it's just a fancy way of saying we want a good dependency management that is self-contained. If you look at what a reproducible experiment looks like, it's a spectrum all the way from not reproducible at all to the holy grail. The first thing, you need to be able to store effectively your data, so your model in this case, for example. Metaflow already does this by storing it in Metaflow artifacts. It persists to S3, which sticks around. Then you need your code, what you do with your data effectively. So we already do this. Metaflow stores your code as a Metaflow package, again in S3, so it's accessible later. You need version control, so you can refer to it, which run you did. We have this already. We talked about it with Metaflow run. You have metadata, so you can refer to it like which type of hyperparameter did I use. We have tags to support this already with Metaflow. And this part is about supporting libraries, which is effectively your environment that all of this code can run in. And there's two more things on top that we don't talk about here. You have data, so you can refer to which data you actually need to use. If you use good hygiene here, which most people do, which means that you don't overwrite your tables and you actually append new partitions, for example, you have this reproducible data that you can refer to later. And then, of course, there's entropy. This keynote speaker spoke about cosmic rays. We don't have nearly that problem here, but that's what I'm talking about here. So we can't solve that completely. So how do we do it? We considered a couple of solutions: PyPy, Docker, Mamba. I won't go into too much detail, but basically, the PyPy, you don't really have runtime isolation because you depend on your platform. It's not really language agnostic. It does have a low overhead, and it's a very good solution for people. Docker is great for the first two, not so much for low overhead. It also is hard to use in our Netflix environment because we already run in a Docker container, so it makes it hard to use Docker in Docker. Conda, or specifically Mamba, kind of answered all of these questions in the positive, and that is what we've been using. What does it look like? And you have seen this before in the previous slide, but effectively users can just specify something like this, saying, hey, I want to use PyTorch 2.1.0 and the CUDA version 11.8. And that's pretty much it. Then after that, Metaflow will take care of making sure that this environment is available wherever your code runs and reproducing it there. We also support things like requirements.txt, again, to lower the cognitive overhead for users, going back to one of the principles. That is something that they're familiar with, so they can use that. And we have externally resolved named environments to, again, for the pyramid concept here, where other teams can build effectively environments for data scientists to use, and they don't have to really think about them. You can think of named environments kind of like just tags, like someone will create this PyTorch environment that you can then kind of go ahead and use. From a technical detail, how do we do this? So an environment is actually defined by two quantities. The first one is effectively what the user requests, and the second one is effectively what the environment looks like at the end. So if we have a set of these environments, and we have ones that are already solved, so that means that we know what the user requested and we know how exactly it was solved. We can take this and see, okay, the user wants all these environments. We know all the ones that are already solved. Now we need to solve these other ones. So we take these other environments that we need to solve. We run them through sets of tools that are completely open source. We didn't invent the wheel here. Things like pip, poetry, Condalock, Mamba, whatever. There's a bunch of technology that runs under the hood, abstracted completely from the user. We figure out what packages we need. We will then effectively fetch all these packages from the web, upload them to S3, persist them. Why do we do this? If you run at scale like we do at Metaflow, we realize that some of these sources for these packages actually will throttle you or sometimes will go down. And this means that your environment no longer is reproducible. You can't then fetch those packages from your sources. So we put them in S3, which is a high bandwidth system. and which makes your environment much more reproducible. Once we have that, we also save effectively the metadata for the environment, saying, well, all these packages belong together in this environment. This is where we implement named environments as well, where we can refer it to with a particular alias. And we give it back to the user as well, saying, here are all the environments that you have to solve. And after this, we can effectively run your code. We can reproduce the environment. We can rehydrate it anywhere you run it. We can rehydrate it later. We can say, if you want to access the artifacts from this run, here's the environment that you need, and we'll give it to you. One example to this, how people use this, is through effectively training explainers. In this case, we effectively have flows that train models, and then we want to have another flow that runs that trains another model on the model that was trained in the first flow. And each of these models that were trained, model A, B, and C, have different sets of dependencies. Each data scientist or data scientist group will use different sets of dependencies for their model. We leave them the choice there. Now, when you want to train the explainer for it, you need to not only run in the environment that the model was trained in, and you also need to add your own dependencies, like, for example, SHAP, to be able to train it. So what the user did here using Metaflow environments is effectively, they're in their flow. The first step builds the new environment to train the model. And in the second, you basically say, OK, now I'm going to train the explainer for this model. This is a very simplified view of it. But this is what Metaflow environment allows you to do quite simply. Before this was not possible to do. You had to kind of like really hack around to figure out which dependencies the user had. And this makes it very easy and very few lines of code to make this service run. One more thing. You might think that this is great. If your environment is all nice and contained, then nothing can change. However, the world unfortunately doesn't work quite that way. There are things like thick clients, and we actually have use cases at Netflix where you have like an external service, like a gRPC image service, that also keeps trudging along. And so that service will nicely keep effectively the Netflix managed Docker up to date, saying, oh, these two can talk to each other all the time. But now if you have your own thick client inside your environment that doesn't move because you've locked it in place, at some point it may stop moving, therefore breaking the reproducibility of your experiment. The solution for this is what we call the escape hatch, which effectively runs a subprocess with the thick client on the side and allows you to escape out of your Conda environment. So in this case, your thick client runs through this fake proxy escape and will communicate with the base Python environment that runs on the main image that moves along with the service itself. All right, new topic, Metaflow hosting. David mentioned it earlier as basically the basis over which Amber, which is our media processing framework, works. And I'll explain some of the details here. So Metaflow hosting is, again, a very simple way of having the user be able to express a RESTful service. So this is all that it takes to basically take your code that you have here. Oh, it's not here, actually. The endpoint here, right here, your code to have that put into a RESTful service. It looks very much like Metaflow, so again, it looks very much like Python, and so this is something that you don't need a lot of cognitive overhead to figure out how to do. I'll go over both the initialize and the endpoint specification in the next few slides. At a basic level, like I mentioned, you basically can do any code that you want in your endpoint. And you can load any artifact that you want. In this case, you can load something from Torch. This, as we'll show in the next slide, is also tied to Metaflow, though. The typical use case is that you will train your model in a training flow, and then you will host it using this and allow users to basically access it to do real-time inference. So defining your Metaflow service, there are two main parts. The first one is the initialized part, where you basically say, what does my service want? So in this case, going back to the dependency management that we just talked about, you can link it to an environment saying, I want to use this environment. This is the same environment that you can use for training, for example. So this makes it very easy for users. We have region support. This is for internal use since we run in multiple regions. You can specify resources that you want for your service, and you can specify some scaling policies as well. We don't need the user to tell us more than this, and we will take care with this basically of scaling their clusters up and down depending on their usage. You can also specify cost-saving measures or like how long you want it to keep up. That's pretty much all you need to specify your service. The next thing is you need to specify what your computation does. It is similarly simple. You specify a name and a description, which can appear in a Swagger page to let your users know what your service does. You specify the methods for the rest things that it needs to do, and some schemas that will be enforced and checked as well. And then you can specify any arbitrary Python code, nothing special required. You return your payload, and that's all that you need to do. Deploying it, if you tie it to a Metaflow, so this is a regular Metaflow flow as we've seen it before. So this will, for example, run on a daily schedule in the Maestro workflow. So this is like you can retrain your model and then deploy it every day. You specify your environment. This is your artifact, your model that you're training. And then you specify, OK, I want to deploy this model. You say, I want to deploy whatever happened in start. This is how long I want to wait for the deployment to happen. Some audit functions. So this allows you to basically verify that your model is actually valid. You can specify any arbitrary audit function here. And then you say, OK, now I make this visible to my user. That's it. That's pretty much it. So users basically use this, and they can have an entire flow where they train their model, and then they deploy their service to endpoints, and then consumers can start using it right away. And so for users, this has been really easy because they really don't have a lot to do, and all the infrastructure under the hood is completely hidden out and taken care of for them. Out of the box, they get request tracing, they get metrics, they get dashboards, they get auto-scaling, they get Swagger, they get logging for free. The example for this is effectively Amber. So Amber is a system that is built on top of Metaflow hosting, which sits here. It will basically, Amber will take movies and then features that need to be computed on those movies and then send them over to Metaflow hosting. Each feature will be running effectively as a service. Metaflow hosting will take care of scaling the service up, getting the request from Amber to the movie, processing the request, and sending it back. One of the things that this slide shows is that Metaflow hosting actually supports both with the exact same code that you saw earlier, synchronous request, as well as asynchronous request, which is what Amber uses here, because some of these requests can take a really long time to process. So they are done in an asynchronous fashion. Next, David will start off with some of the in-flight work that we still have going on.
So we started working on Metaflow hosting circa 2018. And back then, we already had this other idea called Metaflow functions. And what's the problem that we want to solve here with Metaflow functions? So this is work that's ongoing right now. It's actually what I'm working on this quarter. So this is not complete by any means, but we do hope to put it in the OSS. Anyway, the idea is model relocation. So you train a model in Metaflow, but then I actually need to use it in all these other contexts. So it might be my own workflow that does some sort of a bulk scoring, like I had shown during the data section. It might be another user's workflow that doesn't know or care about the details of your model, like the dependencies or anything like that. It might be some other Python environment, like a Jupyter notebook, or it might even be the Metaflow hosting that Romain just described. Now, this problem of relocation gets even trickier if you are working in a large company like Netflix. You know, it's not just us working on a machine learning platform. There's a large team. And in fact, some of that team implements their systems in different languages. So we have a large Java Scala stack to do feature engineering, model serving, and some offline inference. And so how do we share code from Metaflow with all of these other systems? Well, the idea here is to make it as simple as possible. We just want the user to express one UX that binds the code, the artifacts, and the environment together and builds a single encapsulation that can be used elsewhere. But you might be wondering, wait, I thought this was microservices were for. We just talked about those in Metaflow hosting. The problem with a microservice is it actually adds a new UX, right? It adds a communication protocol on whatever your core computation was, like REST in the case of Metaflow hosting, or gRPC. And that sort of mixes two concepts together that we would like to be separate for the user. It's also possibly inefficient. It's choosing a runtime, a networking runtime for you that may not be appropriate for all of those different relocatable scenarios. So let's take a step back and do something really simple. What if we allowed some syntax here with this @function decorator, which is telling, the user is telling us that this function that just adds two numbers together is going to be a part of this system. And what if we could export it someplace? And this would package up, using all of the same mechanisms that Romain described earlier, package up the dependencies, package up the code, and create a little metadata file that describes this function. Now, any other system can read that metadata file, which tells you how to pull the package and recreate a little local runtime. So after importing the function here below, you're not actually getting the original function. You're getting like a proxy object to it. And that function is actually running in its own subprocess, which encapsulates the environment and all of the other properties that Romain had mentioned in the previous slides. Now, what about more complicated scenarios? Don't we want to take things that were trained from Metaflow? So let's take another slightly different version of this adder function that takes a Metaflow task as one of its arguments. Now below, we can use our client to say, grab the latest run from my flow, refer to one of the steps, and grab that task object. That task object contains all of the data artifacts, like the model and all of the environment. And we have this fun little syntax where we can bind that task object to that function. It works like currying or other things that you've seen in other systems. It basically creates a new function back that removes the task, and you get that same adder function that you had seen previously. Now, the user of your function is completely unaware that you have bound this task to it and provided some information that wasn't available through the arguments. We'll just give a little hint of the architecture. As I had mentioned, we rehydrate your function in its own conda environment. So this is the user's process, Python process. This is our internal Python process. We have a ring buffer shared memory interface, and we use some certain Avro-based deserializers and serializers to pass the data back and forth. I had mentioned that this is also meant to work in cross-platform. So you can take that same diagram that I just showed, and you can add any other layer on top of it. If your language has good POSIX-compliant shared memory facilities, you can go ahead and implement a direct memory map interface to this function, very highly efficient. If that's inconvenient, you can implement a REST or a socket or a gRPC communication layer on top. Romain's going to tell you just a little bit about how we're thinking about improving our developer experience.
Thanks, David. So yeah, the last section here on this talk is effectively developer experience. So Metaflow has been really useful in getting from the laptop all the way to production, as David mentioned earlier. But one of the things that users have been telling us is that still that first step of going from your Jupyter notebook, for example, your ideation stage, to your Metaflow flow is not always the easiest. So that's what we want to try to improve. And again, this is very in-flight work. Some of this you'll see it appear in open source in the next couple of months, most likely, and some will take a little longer. What we want to improve, though, is effectively the development cycle that users go through. So usually, you will start developing your code, and particularly if you think of a Metaflow flow, you will probably focus on a particular step first. You will start developing your step, and then you will execute your step. Is there like a fire alarm or something? Okay. No one's burning? Great. So we'll execute the step, and then you want to validate whether your execution is correct, and you'll make progress, probably either iterate on that same step, and at some point you might move on to the next step. Once you have your whole flow that's working, you'll want to productionize that through some sort of CI/CD pipeline. So you'll push out your flow, there you'll have effectively some tests, and you might have some configurations where you want your flow to be deployed in different manners. This is extremely common at Netflix, and I'm sure in other companies as well. If you take, for example, the CDM example that the content demand modeling that David talked about a little earlier, they will effectively have different metrics that they're optimizing for that they need to calculate. But their flow looks very similar. It will use different tables, it might use different objectives, slightly different metrics, but most of the structure is the same. So ideally, they want to deploy develop this flow once, and then kind of configure it to different configurations. So you'll take all those and deploy multiple flows. So we want to improve this whole cycle, both the first one where you're basically iterating and developing, and then the CI/CD part where you're deploying. So the two features that we have upcoming for this, the first one is called spin. The name may change. We may spin on it a little bit. But the idea is to iterate on a single step quickly with a fast local execution. And then once you're done with that, you can iterate on your next step using the result of your previous step in that next step. So you can kind of build your flow step by step. And once you have the whole thing, you'll be able to then ship it over to production. This will actually also be useful if you think about it, just for debugging a particular step that has run. You'll be able to say, okay, I just want to debug this step, just execute it really locally, make the changes quickly, and re-execute that step. Right now, that is not very possible. You have to kind of re-execute the whole flow, so it's kind of annoying for our users. And the last one that should be coming out soon is the configurations. And will be very simply, well, you'll have deploy time, static parameters that you can define in some sort of file. And those values can be used anywhere in your flow, in the decorators and parameters, steps, etc. Yep, I'm almost done. Thank you. I hope you enjoy this talk. Please come find us here for this week. Otherwise, we're on chat.metaflow.org, which is the open source Metaflow support. I think we have 5 minutes for
Thank you.
Thank you. That was 45 minutes. Perfect.
Yeah, so according to the schedule, we still have 5 minutes for Q&A. I'm trying to find out if the fire alarm is actually going off. They're saying we don't have to evacuate yet. So we're going to take some questions. There's another microphone in the back. Raise your hand if you have one. The one I just wanted to clarify, you had a slide about I can run this locally, I can run on a server, and here's where the instructions are for how many cores and memory or the scheduling. Does that all just get ignored when you're running it locally? Those are only applied for Maestro?
That's right. The decorators have different contexts, and they're aware of their contexts, and they'll apply themselves as needed in the correct context.
I was hoping my laptop was suddenly going to have 64
No,
cores.
we didn't increase the RAM on your laptop. Yeah.
Dang, that would have been amazing. That would have been a great talk. Any other questions for...
Okay, so again about resources and auto-scaling. So if I determine that my model needs a certain amount of resources and that's incorrect, right? I tell you it needs, 64 cores, whatnot. And actually it needs 128 or it needs, 2. What is done on, I guess, what is abstracted away to increase performance for that throughput?
So, okay, there's actually 2 cases here. The first case is you tell us that you need more and you actually need less. And at that point, it's not a functionality problem. It'll be a resource problem. We do, and Netflix has become more concerned with resources, especially with large language models these days. We do try to surface this to the user and give them hints like this, took too much time, or took too many. You asked for this many resources, but you actually only needed this much. So maybe tweak it around. But we don't prevent users from doing that. We try to provide a platform that can give them as much information for them to do their jobs. On the other case where it won't work, then unfortunately it will break, and then users usually come to us and say, okay, what happened here? And we kind of help them solve the problem. But you're right that effectively we can't abstract everything away, unfortunately. We did explore at some point whether or not we could kind of auto-tune the resources, and there's some research that's going on there. There's some cases at Netflix where we do that. Actually, there is one interesting blog post that you can find on the Netflix Medium blog that goes about tuning resources for Spark jobs depending on their failure characteristics. And actually, the tuning algorithm that is used uses Metaflow, so it's kind of funny. But it's not Metaflow that's tuning itself, but it's Metaflow used to tune something else. But yeah, unfortunately, not everything can be abstracted. I don't know, Dave.
One thing that we do provide is some automatic visualization. So we have a Metaflow UI that can show you characteristics about your individual runs and tasks. And in those visualizations, for instance, if you use a GPU, we automatically embed some GPU statistics in a graph and warn you if you're underutilization, for instance. It's kind of we definitely have a notion of freedom. We would rather people do their work and use too many resources, because again, I mentioned that people time is actually more costly than machine time. We can always, if a project, in the best case, a project is successful, that's fine if we go back and tune the resources a little bit manually.
Well, that's all the time we have for questions. Give another thank you to Dave and Romain. Thank you.